Lab 12, Conservation of Collisions.
Welcome to our final physics project. Today we're going to talk about the concept of conservation in collisions. This is from lab number 12. Our main goal in this experiment was first to experimentally verify the universal law of conservation of momentum, and second, to explore the contrasting behavior of kinetic energy in two specific types of collisions, elastic and inelastic. To conduct this experiment, we utilized a specific set of equipment. The core components were the low-friction track and two collision carts, which could be fitted with magnets for elastic collisions or Velcro for inelastic ones. We used two Pasco motion sensors connected to a Pasco 850 interface and a laptop running the Pasco software to accurately record the motion data. Finally, we employed 500-gram weights to change the mass of the carts for one of our trials. For our setup, we used a low-friction cart track with two carts and a pair of Pasco motion sensors. The sensors were positioned at either end of the track to accurately measure the position and the velocity of each cart just before and just after impact. We then utilized the Pasco software to calculate the key quantities, momentum, velocity, and kinetic energy for each cart, and then determine the total values for the entire system. In physics, a collision system is considered isolated when there are no net external forces acting upon it. While our track isn't perfectly friction-free, we focused our analysis on the very brief time interval surrounding the collision, where the internal forces of impact are so large that the small external forces like friction and air resistance become practically negligible. Now let's proceed to the core concepts, the specific method we employed, and the compelling data we gathered.
This laboratory exercise is founded upon two essential principles of classical mechanics, the conservation of momentum and the conservation of kinetic energy. Momentum is a fundamental vector quantity defined by an object's mass multiplied by its velocity. The core principle governing collisions comes from Newton's third law. The two colliding carts exert forces on each other that are equal in magnitude but opposite in direction. This means the change in momentum for the entire system, known as the net impulse, must be zero. Consequently, the total momentum of the entire system must be conserved. This conservation law holds true universally. Therefore, we predicted that the total momentum before and after the collision would be theoretically identical for all three of our experimental trials. There are two in which kinetic energy can be explained. Kinetic energy is a scalar quantity representing the energy of motion. Its conservation, however, is conditional on the two different types of collision. In a completely elastic collision where objects bounce cleanly with no deformation or energy loss, kinetic energy is conserved. In a completely inelastic collision where objects stick together, a significant amount of the system's initial kinetic energy is converted into other non-mechanical forms, and thus kinetic energy is not conserved. We designed three specific scenarios to test these concepts. Trial 1, elastic. We used two carts of approximately equal mass. Cart 1 was stationary, while cart 2 was rolled onto it. The carts utilized their magnetic bumpers to ensure an elastic bounce-back collision. Trial 2, elastic. Again, using equal mass carts, both were set in motion, rolling directly towards each other for an elastic collision. This high-impact case allowed for a precise measurement of momentum transfer. And finally, trial 3, completely inelastic. Here we used unequal masses. Cart 2 had an additional half kilogram weight. Cart 1 remained stationary. The carts used Velcro bumpers to ensure they stuck together and moved as a single combined unit after the impact. This provided a perfect test case for an inelastic collision. By comparing the initial and final totals for both momentum and kinetic energy across these three critical scenarios, we aim to provide strong experimental evidence for these fundamental conservation laws.
Let's now analyze our experimental data, which provides evidence for our findings. Our primary focus was on the calculated difference, the value after the collision minus the value before the collision. A result extremely close to zero indicates successful conservation. The results for the total momentum across all trials were outstanding. Trial 1. The difference was 0.0399 kilograms times meters per second, a small positive deviation. Trial 2. The difference was negative 0.004 kilograms times meters per second. This value is remarkably close to zero, representing a near-perfect example of momentum conservation. And finally, trial 3, the difference was negative 0.0011 kilograms times meters per second. Again, a negligible difference, proving that momentum is conserved even when the object sticks together. The consistent minimal deviation from zero confirms our hypothesis. Momentum is conserved in all three tested collision types. The results for kinetic energy, the energy of motion, are what separate our collision types. Trial 1, elastic, we lost 0.0167 joules of kinetic energy. This shows that the bounce was not perfectly elastic since some energy was lost during the collision. Trial 2, elastic, we lost a very small amount of energy, 0.0029 joules. This trial was very close to the ideal elastic case, where kinetic energy should be conserved. Trial 3, inelastic, we lost 0.0016 joules of kinetic energy. Even though the numerical loss is small, this collision is classified as inelastic because the cards stuck together, meaning kinetic energy was not conserved. This loss is exactly what we expected when the cards stick together. When they stick, kinetic energy is converted into other forms such as sound, heat, and deformation of the Velcro. Our kinetic energy values clearly distinguish between elastic collisions, where energy is mostly conserved, and inelastic collisions, where kinetic energy is not conserved.
Our experiment worked great, but our numbers weren't perfectly zero. The rules of physics require a perfectly isolated system, which means nothing outside is pushing or pulling. We determined several factors that cause small errors. The first factor was friction and air resistance. So we ran into a problem that a small amount of friction on the track and air created a drag. These are outside forces that slowly take away energy and momentum from the carts. The second error came from timing. We had to pick the exact moment before and after the crash on our computer graphs. If our timing was off even slightly, it changed the velocity numbers, which changed our momentum and energy calculations. And the last error that we encountered was magnet repulsion. The largest problem that we ran into was the repulsion by the magnets that are built into the carts. For the first and second trials, the magnets added additional momentum, helping to push the carts away from each other after their initial contact. This accounted for the majority of error, altering the final velocities, therefore changing the final momentum and kinetic energies. Luckily, the third trial was not affected by the magnets, resulting in percent error of momentum 0.42%. To sum, we proved that the law of conservation of momentum is true for every collision, and we showed that kinetic energy is only saved during a perfect bounce. It gets lost when things stick together. This experiment gave us strong proof of these basic rules of physics. Thank you for watching.